Hello, everyone. Our next speaker is a DevRel and electronics educator, and he's been living out on the edge with AI. But he is here today to tell us why some of the lessons of classical control theory don't need to be thrown over just yet. Please join me in welcoming to the Hackaday SuperCon stage, Shawn Hymel.
Good afternoon, SuperCon. Thank you, Elliot. I have been working with machine learning for a couple of years now, doing things specifically on the edge because it's fun. I enjoy this. I come from the embedded background, embedded world, and I really enjoy the machine learning side, and combining them is a ton of fun. So the last year, I've been working specifically with reinforcement learning, and that is a deep dive in its own realm, and this is a ton of fun because now we're getting into the idea of, can robots not just do a thing you tell them to, but can they learn to do the thing you tell them to? So that's where I've been really excited about, and you've probably seen some of these in the news on YouTube, and you probably recognize a few of these. This is the Disney's new Imagineering robot. If you've seen this, it has a beautiful bipedal gait. It walks around. It's really cool to see. I honestly don't know what they use to make this because Disney controls everything. This is copters. The idea is, what if we can have robots learn to fly themselves? Same idea with self-driving cars. Not just let me program you to avoid pedestrians, but what if it actually learns to avoid pedestrians and it's rewarded or penalized based on that? We also know Boston Dynamics. We're familiar with Spot, Atlas, all these good ones that they're working with. Now, there were a lot of conversations because Boston Dynamics does not publish a lot of papers, if any at all. So there was a lot of conversations over the past few years whether Boston Dynamics actually does reinforcement learning or not. When they had an interview, I learned a couple of days ago, there was an interview with the CEO on the Lex Fridman podcast. They mentioned they do a mix of classic control theory algorithms along with reinforcement learning. So they are actually using some, despite what random Redditors may tell you. Then there's also this last one that came out. ETH Zurich put this really cool robot out last year. They published a paper on it using reinforcement learning. And this is a four-wheeled robot, and it can do things like climb up stairs. It learned itself how to raise itself up and balance on two wheels. This is a cool video. Go check this one out if you haven't seen it. I forget the name of the robot, but just search for ETH Zurich robots. These are really fun. The dream behind all of this, and I want to say Boston Dynamics' dream as well, is I want to go buy like a pet dog, a robotic pet dog. I already have a pet dog. I want a robotic pet dog that I can put on a table, I can push a button, and overnight it just teaches itself tricks or teaches itself to walk. And that's where we're trying to go with some of these, but as it turns out, reinforcement learning is really, really difficult. We're not at that point yet. Boston Dynamics is multi-millions of dollars in funding, dozens of PhDs and engineers trying to even remotely achieve this dream of having robots teach themselves and get something close to biology in the way the motion happens. Since I am not Boston Dynamics, I wanted to start with something very simple. Here's me being very proud of myself doing an inverted pendulum. Who has done an inverted pendulum project? A few people. Did you do it in school? Keep your hands up. All right, who did it on their own just for fun, like outside of school? Oh, like at least one, okay. Well done, well done. This was me doing it outside of school because I never took a control theory class, but apparently this is the thing you do when you do a control theory class. One of the projects, usually your end project, you learn all about control theory, control loops and all of that, plants, what have you, and you do an inverted pendulum. It might not look exactly like this, but the idea is to have this thing balance and do it in such a way that you don't have control over the primary axis here. So in my case, this is a kit. I know I'm losing like maker cred because I didn't build my own balancing bot here, but the reality is I just wanted to get working on the algorithms. So it moves back and forth, and the idea is just by moving the stepper motor on this axis, it controls the pendulum that's on this axis. And this is a quadrature encoder that measures the angle. And so the hope is that you move it back and forth, and the real goal is to have it swing up and then stay balanced. And that's the goal. And the balancing part was actually fairly straightforward using a PID controller. You can get it, apparently, to do the swing up if you do a nested PID controller or some of these more advanced ones, linear quadratic regulators, model predictive controls. Not that I know anything about those, because I just played with the PID side. But you can get it to do the swing up and hold there. So this is a solved problem. This is nothing new. Like students are doing this like freshman, sophomore, junior year in their college courses. I wanted to make my life hard, so I went and used AI to do it. Can we have a robot that learns to do the swing up on its own? So a little bit of history, not really history, but background behind reinforcement learning. Here's the essential diagram that if you look up anything with reinforcement learning, you will see. There is an environment. That is the world. That could be a virtual world. That could be the real world. That might be the rules of the game chess, or maybe Go. We have some sort of interpreter that gets observations from that. And in our case, our observations are going to be 4 values. This doesn't work very well with 4. 4 values. And we have the encoder angle, so that's my quadrature encoder. That's the angle of the pendulum. We have the angular velocity of that encoder. How fast is this moving? We have the stepper motor. I want to know the position of the stepper as it relates to where it started, the relative position, and that angular velocity of that stepper motor. Those are the 4 values that I'm going to look at for my observation. Those get fed into my AI agent. This is the decision-making body. This is just the code that says I take observations in, and I give you some sort of action as an output. In this case, I started with continuous action space. I said, figure out how much you need to move that stepper motor by in order to achieve some goal. In this case, the goal is swing the pendulum up and balance it. To achieve that, we need to create a reward function, and this is the interpreter is in charge of taking those either observations or some other part in the environment and saying, based on what I see, you get some sort of reward, so we incentivize the agent to learn to do something over time. And the agent not just wants to maximize, this is the tricky part of reinforcement learning. The agent doesn't want to maximize the reward from taking one action. It wants to figure out which action to take in order to achieve maximal rewards in the future. Probabilistic rewards in the future is where AI gets very tricky. Actually, our brains are really good at doing this already, with some hiccups here and there, but we're generally good at maximizing our rewards and can predict into the future with some probabilities involved in there. And so the idea is let's create math to do that for us, and now we have robots that can learn, or AI agents that can learn. So here's the reward function that I used. This came right out of Farama Gymnasium, their whole framework for doing reinforcement learning. And this is the reward function, so we just square the angle of the encoder, we square the angular velocity, we square the angle of the stepper motor, and we square that velocity, and then put some constants in there. The constants tell me that I care most about trying to get that pendulum upright, hence that 1, and everything else is kind of secondary to that goal, or even tertiary on that side. The hope is that I want to get the pendulum up and not moving as much as possible, hence why I care about angular velocity. And so that negative sign says that every step, you're losing points. So 0 is the best you can possibly do for any particular step during this process, and anything other than that, it's going to be negative, so it's going to incentivize the agent to quickly as possible try to solve this to make this 0. And so I've normalized it, so the angle of the pendulum is 0 when it's up, and it's either 1 or -1, but because of that square, it doesn't really matter when it's down. And then same with the stepper motor. It's 0 where it starts, and then 1 or -1, 180 degrees past. And there's this hard limit that says if it rotates a full 180 degrees in either direction, stop the episode, and you get penalized pretty hard by 500 points. And the reason for that is because there's this cable that comes off here, and as you can see, that gets nicely turned up. If you come find me later, I'll show you this. I don't want to get into why there's a whole bunch of stuff here, because I had to resolder it because I started breaking internal wires, and then I had to put this nice little strain relief on here. So this was a problem that I had from doing this over and over again. Even with this, the motor skips some, and it still tangles itself up, which is not a lot of fun. But it was good enough for what I needed. I used the proximal policy optimization algorithm, which is considered state-of-the-art. The paper for that was written in 2017. It's still used today for a lot of things. It works with continuous action spaces, discrete action spaces, continuous observation spaces. It's pretty robust, but as you'll see, it's not great. We're still not there yet. With state-of-the-art. You can find this, I use the Stable Baselines 3 framework, which has these algorithms, and then I had to go through this whole process of optimizing hyperparameters. So if you're familiar with machine learning, hyperparameters are anything outside of your model that you can tune that doesn't get auto-tuned. Things like learning rate, how big your actual model architecture, and there's a bunch of stuff in PPO that you can tweak and tune. Reinforcement learning is very sensitive to hyperparameters. I mean, like, you move something by like a couple of percentage points in one way or another, and your algorithm goes from not working to working, or vice versa. So it's very sensitive. So tuning hyperparameters became a whole thing. I use Bayesian optimization using the AXE framework. I won't get into the specifics of that. Come find me later if you want to talk about AXE and why it's actually kind of slick, or weights and biases. But speaking of weights and biases, it didn't work, which, you know, it doesn't work on the first time. Not with anything that's fun, right? So what I'm hoping to see here is each one of these lines is a trial where it has a number of steps, and this could be any number of episodes. And so it just, even though an episode might end here, it just keeps going and keeps counting the steps up as that algorithm is updating and learning, that agent is updating. My hope is that each one of these lines, some of these lines, as it would get better and better with the hyperparameters, because each line is its own set of hyperparameters, I want to see them going up and to the right and approaching 0, because it's the reward that it gets. I don't think this is not cumulative reward, because it'd be going down. It's reward per step. I want to see this going up towards 0 as it learns to kick that pendulum up and balance it. Okay, so why did it fail? We got to talk about some reasons why this failed. First of all, this round trip loop, because I don't think I mentioned it, but the training portion on the agent was happening on my GPU, was happening locally on my laptop. This interpreter is an Arduino, and the action taker is also an Arduino that's controlling that stepper motor. So it's all going through serial over USB, which even at a megahertz, or million bits per second, it would take over 30 milliseconds to go to the agent, do any sort of updates with that stable baselines, and then come back and perform that action. And based on my very, very particular testing, or like, you know, generic testing, empirical evidence, you need lower than 30 milliseconds in order to get that to balance. So the best hope I had was like, maybe I could do that swing up, but balancing right now isn't possible without like tearing apart stable baselines. With the 2 months I had for this project, it was not gonna happen. Also, continuous action spaces are notoriously difficult in reinforcement learning. So we are going to reduce that scope and change how we maximize that reward. First, all I care about is doing that swing up right now. I'm gonna say, okay, I'm gonna put off the whole balancing part for later and come back to that. Let's just prove that we can do reinforcement learning and get it running on a microcontroller, just to demonstrate that. So the first thing we do is we add this area, about plus or minus 5 degrees from the top. If it reaches that and it's not going too fast, we'll call that good. That's a win. Let's restart the episode, give it some reward to incentivize that. If it goes too fast in that area, then we're gonna say you've crashed. We're gonna penalize the agent, and we're gonna start over. Okay, so we've reduced the scope for this. The other thing is now we can start talking about, let's just change this to discrete action space. Instead of that wide range of minus 60 to plus 60 degrees that you can move the stepper by, you only have 3 possible actions. That's minus 10 degrees, do nothing, or plus 10 degrees. This worked a lot better. So after a few trials with good hyperparameters, we can start to see it's approaching 0. Okay, something's actually working here. So now that we have something trained, we have the RL agent, we can go and look at what's the actual decision-making body, and that is the actor. This is an actor-critic network, if you've heard of that. PPO uses an actor-critic. It's 2 different machine learning models, or 2 different neural networks, dense neural networks, 3 layers each, 256 nodes in each layer, and the actor's in charge of taking those 4 observations and then giving me an action to perform, so hence the 1x3 down here. This is the actual network, by the way. I put this into Netron and just took a screenshot of it. And so the 3 here is my values, just generic logic values that I get for minus 10, 0, and plus 10. So you figure out whatever one of those is the highest value, and that's the action you should perform. The critic, on the other hand, is a regression model. It gives you 1 value out, and it's used during training to try to predict how much reward do I think I'm gonna get in the future. And it's used as part of that training process. But the good news is once we're done with training, we can just get rid of that critic side, and we just take that actor. And once we have that actor, we can go ahead and deploy it to the microcontroller. I'm just using Arduino because I'm lazy and it makes my life easy. There's a number of tools you can use for compression and optimization. I know Edge Impulse very well, so I'm going to take my model here. I'm going to use Edge Impulse to help me compress and optimize that for an Arduino and deploy it to an Arduino. I used an ESP32S3 from Seed Studio because those are very fast, very powerful. They have neural network optimized hardware in them, which is super cool, and I love to see that. So we have the loop now. This happens inside the Arduino, no more CPU or GPU down here, but notice I took away that reward function because we don't need it anymore. We're not training, we've deployed it, it's trained. Okay, this is the fun part. Live demos, okay. So first thing I'm gonna do is I'm gonna give that stepper motor 18 volts and avoid the feedback from the microphone. All right, come on stepper motor, you got this. Come on thing I bought off of eBay, or not eBay, but Amazon. There we go, 18 volts going to that stepper motor, and let's power on that micro. All right, remember this is AI doing it, not a control loop. Yes, it did the swing up, hooray! I know it's fairly simple and fairly straightforward, but it gives us a way forward to prove that yes, we can run reinforcement learning algorithms on microcontrollers. Yes, it's a solved problem, but now I'm doing it the hard way, and it taught itself how to do that, which I find really cool. This is in case it failed, which it didn't. Here's some of the output. If you look at this, the observations that it's collecting, so this first one is the angle of the quadrature encoder. This is the angular velocity. Remember, it's been normalized, so minus 1 means it's pointing down, 0 means it's pointing up, so this is an example of where it worked. We have the angular velocity, we've got the angle of the stepper motor, which it does a pretty good job of staying pretty close to where it started, and then the velocity of that stepper motor. We also have the time between the steps, and the interesting thing here is the inference time is about 8 milliseconds, which is pretty good for that 3-layer dense neural network. And you'll notice that it actually waits for the stepper to complete. So if it was minus 10, which is one of the possible actions, then it waits for that stepper to complete. But if it's not doing anything, then we do 8 milliseconds. Honestly, I found that waiting for the stepper to complete was a lot easier to deal with, because if I tried to create a new inference action while the stepper was doing its thing, it would just start skipping and freaking out. I didn't tune the stepper motor to do that. It has an acceleration and deceleration time, and it would skip like crazy when it did that. So where do I see this going in the future? And actually what we're doing right now is there's a number of frameworks like NVIDIA, what was Isaac Gym is now Omniverse, and we also have things like Unity where we can create virtual simulations of this, train the algorithms in there, and then deploy them. This gives you the advantage of creating thousands of copies, and I can train in parallel, which is nice, it's faster. And the big issue with hardware is it's very hard to reset. This is great because a stepper motor, I can just say go back to home, but think about like a rover or something. Like, what do? You have to like pick it up and move it over somewhere when it's done with the episode, or you have to like train it to go back home, which is like defeating the whole purpose of having it trained. So that's a problem, and the virtual environments solve that for you. So where we're going, where we're at now, and I've got my friend Dimitri, who, let's see if this works. So he was actually working with the Biddle, which is the little $250 spot-like dog, and he was doing this in a virtual environment and training them to actually walk or scooch along. When I gave this presentation to a group, including him, on Wednesday, he was like, oh, I was working on this. He sent me this video. I'm like, oh, this is so cool. He's like, but I never got it working on the hardware, and you just solved the hardware problem. So he came from the software side of simulating it. I'm coming from the hardware side of like, can we finish the training in the hardware? And hopefully together we can make a tiny Boston Dynamics team. Yeah, right. But that's where we're getting. I'm hoping people can use this and create their own robots using reinforcement learning. So I'm way out of time. I don't know if we have time for questions. Maybe. I'm looking at Angela, who's the next speaker. 5? Okay, couple of questions. My repo's up here. If you want to see my code, it's a mess. I apologize. I usually make better repos, but I was finishing this up like a weekend ago. But follow me on any of the social media platforms. Reach out to me. I'll be walking around after this, but we have time for a few questions. You talking about doing for? Are you saying doing the training loop in the Arduino and then evaluate or update after? Yes. So that's actually that thought occurred to me as well as like a way to do this, and so you could get that better latency time, was to have it do latency here, basically do your Monte Carlo simulations, collect your data from that, update the model, and then reflash the ESP so that it can do more like what we call simulations, but actual episodes. But yeah, that's a great idea, and hopefully that would fix the latency problem. Yeah. Yes. So it's collecting data and rewards at each time step, but reinforcement learning, what it tries to do is it says, I receive a real reward, but based on my knowledge of the universe and what I expect, what's the probabilistic or expected value based on an action that I'm going to take? Not that I'm going to get a good reward next, but I'm going to get a good reward until the end of the episode or until infinity. And so it's trying to maximize the future expected value of the rewards. Does that make sense?
Yeah, how does it compute the future value?
It does it by trial and error. So it has to do a whole bunch of stuff where it just tries random things, and it says, well, based on what I did and the rewards I received, I think that if I do these in the future, I can maximize my rewards. And then it updates the model based on that, and then it just tries that. And so it's an iterative process as you get better and better at approaching that local optimum of saying, now I'm maximizing my rewards in the future based on previous things that I've done and learned. Does that help? This is why it gets like really weird in reinforcement learning. It's all probabilities. No, because the processor is actually fast enough for the training portion of it. I was using a GPU. The problem was the training framework I'm using, like stable baselines and all of these. I don't have much control over what they're doing, so you'd have to strip all of that away and rewrite it. You also run into issues where you're moving memory back and forth to the GPU. So to be able to do your updates and get under 30 milliseconds is a problem, hence that gentleman's idea of let's do our simulations or our trials on the device itself and then train, like take the model, take what I learned from that, and then train elsewhere, and then update the model. It's because we want to close that latency loop. That's the big issue. But it's not a processor speed problem. If you're asking what would it take to train on here, you probably don't want to, because like even getting like a Raspberry Pi, which is relatively way more powerful than this, to like train on like MobileNet, it takes days. It's usually pretty silly to try to train on embedded systems. There's work being done, so you have like neuromorphic processors, which can actually update its own weights. So there's some work being done to get something like that happening, but we're still a ways away from that right now. All right. Yeah. Oh, sure. That was a fun rabbit hole. So there's three big algorithms that are used for tuning hyperparameters in an automated fashion. Well, 4 if you count manual. Like, I really know this algorithm, I know what I'm doing. If I tweak this, this will happen. So there's manual, where you really know the algorithm very well. And there's 3 main automated ways to do that. The first is called grid search, where you just like take a wide range of your hyperparameters and you just like every possible combination, you exhaustive search it, and you're like, whatever gave me the best evaluation, go with that. Very time consuming for something like this, where it could take like 3-4 hours just to run one trial. There is random search, where you take a random smattering of those combinations, and then you do some math to say, oh, this is kind of what it looks like. I think if I kind of go between these, right, you can like interpolate the values to figure out where you might go. And then there's Bayesian optimization, where it actually performs, it uses Bayesian inference to say, Bayesian inference to figure out, based on what I've seen, I have an idea. It basically creates a random probability of what the output should be or could be, and then as you take sample points, you start to get a better idea, probabilistically speaking, of what that function looks like. And so you can say, oh, from here, go to this point and try another trial, go to this point, and you basically start getting towards the optimum set of hyperparameters. What most ML engineers will do, they'll start with random search because it's not exhaustive, and to narrow the scope, and then they'll do Bayesian within like a smaller range. Sure. All right. Thank you, everybody. Come chat with me about RL stuff.